Hello, my name is Yan Li. Today I'm going to present our paper on resilience analysis of cyber-physical network microgrids with communication latency. This is a collaborative work between Penn State University, Argonne National Labs, and the synthetic propulsion technique. If you have interest in our detailed research or collaborating with our team, we are very happy to discuss details with you. So first of all, let me briefly introduce our research motivation. We know resilient operation has become one of the major concerns in power engineering. One promising solution is to interconnect multiple microgrids together to form networked microgrid system. The operations of the network highly depends on the timely information exchange between subsystems and the control centers through the communication network. However, due to the integrations of power electronic interfaces, the system usually have very low inertia, so that our system is very sensitive to disturbances. So the disturbances from communication network also significantly impact the resilient operations. So how to efficiently analyze the impact of communication latency on the physical system's operation is a very challenging problem. In this work, we propose to use the reachability analysis method to quantify the impact of communication network latency on the physical system's operations. So the network latency is modeled by Zonotop, and then reachable set is calculated to bound the system's all trajectories and network latency. More specifically, we can identify critical network latency so that we can better design and manage the communication network for improving the physical system's operation. So here we give you a test example to illustrate our idea. The test system is a typical connected microgrid system. So we have 6 networked microgrid as shown in this left figure. And in the test system, we open the circuit breaker 0 so that the networked microgrid system is operating in the islanded mode. And we use the control system to operate the unit in the system as given here. And we have 2 test cases. In the first case, we study the communication latency's impact on single distributed energy resources. And more specifically, we look at the communication network latency on battery 31. So here on battery 31. And the result is given here. So here we give you several reachability calculation results. And the first one, actually, if you look at the figure, the green region show you the communication latency range is within 50% variations. And the different color zones show you different communication network latency. And the last one also give you the time domain simulation verifications. So from this result, we can see as the disturbances of communication network latency increases, the dynamics is gonna become larger and larger, and eventually our system could diverge. And here is the second case. In this case, we consider multiple communication latency on DR units, and more specifically, we look at the communication latency on battery 31 and fuel cell 33. And here is the simulation result. Different color zones show you different reachable set. And from this result, we can see there is a critical communication network latency. Within this latency, our system can maintain stable operations. But beyond this communication latency, most likely our system is going to lose stable operations. And in this specific case, the critical operation point is 500 variations of the baseline communication latency. So here is our conclusions. So by using reachability analysis, we can efficiently quantify the impact of communication network latency with a large variations of communication network. And the dynamic system can also be efficiently analyzed and evaluated subject to disturbances of communication network latency. And for the future work, we can talk on the distributed calculation to enable a more efficient calculation and analysis. Thank you.